Good evening, everyone. Am I audible? Hello, am I audible? Yes. Okay. So, a warm welcome to all the participants on the third day of our 6 days online Atal Faculty Development Program on advanced topics in AI and machine learning. We are excited to continue our journey of learning and growth together. Today promises to be an engaging day, and we are glad that we are here to be a part of it. Today, we have two sessions, one on recurrent neural networks and the other on deep learning for NLP. So we feel privileged to be such a distinguished speaker with us today, Dr. Gina Kandi. We thank you, Madam, for kindly being the resource person for this occasion, and we fully appreciate you finding time to be with us. Thank you, ma'am.
Thank
It
you,
is
ma'am.
an honor for me to give a brief introduction about her accomplishments. Dr. Gina Kandi is working as an assistant professor at the Department of Computer Science at Cochin University of Science and Technology, CUSAT, located in Kochi, Kerala. She holds a doctorate in computer science and engineering, specializing in the field of natural language processing from National Institute of Technology, that is NIT Calicut. Dr. Gina has been awarded with MTech degree in software engineering from CUSAT and BTech in computer science and engineering from the College of Engineering, Talasheri. She commenced her career as a project engineer at Wipro Technologies in Kochi back in 2007. In 2011, she embarked on her teaching career at Chinmaya Institute of Technology, Kannur. Dr. Gina worked as an assistant professor at Amrita School of Computing, Amrita Vishwapeetham, Ettimadai, before returning to her alma mater, CUSAT. Dr. Gina teaches computational linguistics and deep learning for natural language processing to computer science postgraduate students. Being passionate about recent developments in generative AI, she has introduced a new course on large language models, that is LLM, recently in the computer science curricula. She also has experience with delivering many invited talks and technical sessions at various universities and colleges across Kerala on AI and language processing. I request all of you to please join me in welcoming Dr. Gina Kandi to share her knowledge in recurrent neural networks. Ma'am, you are welcome. No, ma'am, you are not audible. Please unmute, ma'am.
Sorry. Okay. So I was just thanking you for that wonderful introduction. I'm also very happy to be part of this FDP, and I'm very happy that you invited me. And I see a very huge number, 156. It's a record at this time, like 6 o'clock. People are online to study.
The number will increase.
Happy to see that. Very enthusiastic participants. Yeah, at 6 o'clock itself, there was about 100, I think, when I joined. Okay. So thank you, ma'am, for inviting me. That is what I said when I was on mute. Okay, thank you. Okay, thank you, participants. As I said, 156 is a really huge number, and I'm very glad that you all are here to learn about NLP. So before I start, since this is an online session, I would like to request all of you to give a very interactive session so that both of us don't get bored. I don't get bored talking and you don't get bored hearing to me. So please try to be interactive. I know it is too much to ask at 6:30 in the evening, but still, try to be a bit interactive. And maybe I like to know the audience. Like since this is an FTP, I'm expecting most of them would be teachers. But other than teachers, other research scholars, maybe can I have a hand raise? How many of you are research scholars? Shyam Sundar. Hello, Shyam. So, PG students, UG students, students are there other than maybe all students can raise your hand. Manju J. Rajkumar. Okay. So you are PG student, Rajkumar? Okay, thank you. I'm sure there will be more students out there, but maybe they are not in a position to raise their hand. See, this is a trick that we usually use to find out how many interactive audience are there. Maybe. So, like, does everyone, like, how, okay, maybe everyone can lower your hand, and maybe I'll ask another question. How many of you have taught or have learned, like maybe an NLP course at UG or PG or any level? Dr. Sandhya Rai. Thank you, ma'am. See, I'm asking this only because I want to know, like, to what depth I can go in the session, and also to what, like, what all should be covered. Like, should I start from the very basics, or should I start from the very basics, or can I go a bit more detail? That is what I wanted to know. That's why I'm asking if you have taught natural language processing class, or if you have attended a course on NLP at your UG or PG level. Please let me know. Or is there any NLP researchers out there who's doing research? Please start from the basics, madam, if possible, of course. Okay. Okay, thank you. Yeah, from the basics. Yeah, I think most of them wants to start from basics. Okay. Okay, maybe that's it. So let's start. I'll just hide my camera and I'll share my screen. Okay, so welcome to Deep Learning for NLP. Before I start, let me just say there is a slight reordering in the topics. According to the schedule, I think the first topic is RNN and family, and second topic is given as Deep Learning for NLP. Actually, one of the, see, RNN is a very generic model. You can use it for learning any sequence, okay, not just languages. It can be applied for time series data. It can be applied for weather forecasting. It can be used for stock market prediction. Like a lot of other applications of RNN is there. But one of the most relevant application area for NLP is application area for RNN, recurrent neural network, is natural language processing. Okay. So I thought maybe I'll just start with the introduction to natural language processing and convince you why RNN is going to be very helpful here, so that it will be a motivation to understand the RNN architecture better. So there is a slight change in the order. We start from deep learning for NLP and then we will move to RNN. Okay. Can someone confirm that my screen is visible?
Yes, ma'am. Yes.
Okay, thank you. So let's start. Okay. So today's agenda is, first we'll start from basic introduction to natural language processing. Then we will just have a quick recap on neural network. I'm sure for the last two classes you have been learning about neural networks, so you already know what neural networks are. And then we will see how this neural network can be applied to solve problems in natural language processing. And in the next session, we will discuss about RNN. Okay. So to give a very generic view of natural language processing. So natural language processing is one of the most important tasks in artificial intelligence. We all know the Turing test when people, like it was said that we can call a machine intelligent only when, or not only when, maybe like one of the criteria which our ancestors thought, or computer scientists thought that something that will define artificial intelligence is when a machine will be able to mimic, like imitation game, if you have seen that movie. So we'll be able to imitate the language processing power of human. So the huge interest in natural language processing, one of the reason is only humans have capability to process language, or that is what they say. We can argue about it on a later date. But as of now, we know that humans are the only like who can have a like maybe a written and spoken text processing capability. Okay, others may be communicating through other means, but language processing is something that reflects human intelligence. And most of the knowledge that is available out there is in the form of text. So because of these two reasons, NLP plays a major role in artificial intelligence. And to solve artificial intelligence, we can use machine learning techniques. There are other techniques also. We can use machine learning techniques. And we know deep learning is a subset of machine learning, or we can call this as traditional machine learning and this as deep machine learning. So machine learning is a subset of machine learning. Deep learning is a subset of machine learning methods. And to process natural language, we can use any of this. There are rule-based techniques, there are machine learning techniques, and there are deep learning techniques. There are different ways to address natural language tasks. And this session is dedicated to deep learning, so we'll be concentrating on this blue section. So we all have been using NLP in our daily task. So usually this is the slide I show to the first year students, not for our teachers, because all of you know when we do a Google search, the Google is able to complete our sentences, like autocomplete. When we search for something very related, things also come up. So if I search for apartment, you can find that the result will contain residence. If I search for buying a pet dog, okay, Google may come up with pet shops that sell fish also. Okay. So all this, so whatever we see today in Google search are called as semantic search. Okay, so it is not like in the olden days when we used to have keyword search, or when we used to have SQL queries where keyword has to exactly match. Such an era has passed by. Today, all those search engines, recommendation engines, advertisements, video suggestions, chatbots, all of them uses natural language techniques, processing techniques to do this. Okay. Then we have Google's Smart Reply, we have Google's Smart Compose, we have spam filters, and if you go to more complicated things, we have Grammarly. So all of us might have used, since we are in academia, I'm sure all of us have used Grammarly at some point of time to write article. I don't know how many of you have noticed this about a feature where you can actually identify what is the tone of your text, right? Where, by reading the text, how do you identify the tone? How do you understand whether the tone is neutral, or whether you sound confident, whether you are writing as joyful, optimistic, friendly, something that is very urgent, and all these that intention of the user is being measured here, right? And whether the thing is formal or informal. So these are not just based on the words you used. Okay, these are not just based on the words you use. Some higher end of intelligence is being applied to identify such subtle or very hidden facts in your text. Okay, this is one application of NLP. Okay, then we have speech recognition in Google, Amazon Alexa, Apple Siri, all this uses speech recognition. Okay. where you identify what is being spoken and convert it into text and then do the search. And we have translation. So this is a very age-old problem in natural language processing. You already know. So other than those common day-to-day activities for which we use NLP, there are a lot of other applications which you might not have thought of. Okay, especially when you are in academia, you might want be interested in some of these topics. For example, prediction of diseases from electronic health records. Okay, these are some interesting research or student projects and all which you can think of. So if you have enough health record data of a person, okay, in India maybe it's not that commonly available, but in many foreign countries they have a strict law that all health records have to be stored electronically. Okay, then we will be able to predict that this person is going to have so and so diseases in the future by processing the doctor's prescriptions and symptoms. Amazon, how Amazon is suggesting products into your profile homepage. Okay, they try to understand the customer's choice, how Amazon decides when they should launch a new product or when they should conduct a sale. Maybe in social media, every social media uses fake news detections. Like every social media uses fake news detections, hate speech. Okay. Uh, is anyone trying to speak? Thank you. So all social medias like Facebook, Instamart, everyone is sorry, not Instamart, sorry, Instagram, everything is used. Every social media is using some sort of fake news identification and hate speech identification technique. So if you make some very bad comments in this, they can automatically identify it and delete your comment. Then there is stock market prediction. Okay, then that's a very huge business usage. Then there is talent recruitment. So, based on a person's profile, they can identify what kind of job may be best suitable for this person, or for a job opening, they may be able to identify what all people can be suggested for this. Even LinkedIn and all, they are using NLP techniques to do this. And there has been some chat bots that can give counseling and advices to um, people. I will not say patients because patients are not supposed to go to chatbots. They should meet the actual therapist. But there are Facebook. Few years back, Facebook had this chatbot therapist. So if you are very hesitant, like if you don't want to go to an actual doctor, maybe you can talk to this therapist, and finally the therapist will tell you whether you have to meet a doctor or not. And you also know that for in many banking, not just banking application, in many applications, the front office people are being and customer service like call centers and all are being replaced by Autobots. So all these are some applications of natural language processing. So what do you mean by natural language processing? It is all about designing or building computational models. Okay, coming up with new algorithms, or maybe you are implementing a model, existing model to solve a new problem. Okay. That is to understand and generate. So NLP is of, we can say it is of two categories: natural language understanding and natural language generation. Okay. So this natural language generation has suddenly become very popular after the coming of Gen AI. After the coming of generative AI, natural language understanding generation has become very popular now. Till now, like when I was doing my PhD, I was trying to do NLU, understanding what is written in the text. And we say it is, we call this natural language processing because we are processing human language. So writing a compiler or doing something with programming language, JSON, XML, HTML, all this does not count under natural language processing. Natural language processing is only when you are processing human language in which is unstructured. And the idea is to get some useful task. So why I have underlined this useful task is because, see, when I say understand, even that word is very ambiguous. Okay, so that even humans don't understand most of the things that is being communicated. Okay, so asking a machine to understand is a very, very high goal, or maybe unreachable goal even for humans. So it is definitely an unreachable goal for missions also. So when we say understand, basically what we mean is, when I ask my Apple City to book a flight ticket, it should be able to do that. That's it. Okay, it need not understand anything else. So why all this fuss about NLP? Okay, why people are constantly conducting FDPs? Why everyone is doing research and all this? Why this is challenging, or what makes it different from other languages? Okay, we don't say that we are doing research in Python language. We don't say that. Yeah, maybe there are people, but we don't see that commonly. So why is people interested in doing NLP, or why language processing is hard? The first and foremost reason is natural languages are very, very ambiguous. Okay. I'm sure everyone here will agree with it. നമ്മൾ മനുഷ്യരോട് സംസാരിക്കുമ്പോൾ പോലും പലപ്പോഴും ഫുൾ മിസ്അണ്ടർസ്റ്റാൻഡിങ് ആണല്ലേ, നമ്മൾ എന്താ പറയുന്നതെന്നുള്ളത്. By the by, is there anyone who doesn't get Malayalam? Okay, I see a few beeps. Maybe I should check.
Yes, ma'am.
Okay.
Ma'am, participants are from all over India.
All over India. Okay, thank you. Yeah, it is an Atal Fdp. I should have guessed it. Participants are from all over India. Yeah. So maybe we'll stick to English. Okay. So see, language is ambiguous. Even when humans communicate, there are a lot of misunderstandings. When you think in the terms of mission, there are a lot of ambiguity that can happen. See, for example, lexical ambiguity. When I say lexical ambiguity, it means ambiguity at the word level. For example, when I say meet me at the bank, okay? Bank, BANK, bank. Bank is a very ambiguous word. Bank can be a financial bank. Bank can be river bank. It could be a power bank, right? It could be a blood bank. So bank, the word bank itself is like not just bank. There are many words out there which is ambiguous. Okay, maybe I can say the word cell, CELL, cell. Okay, when a physics person says cell, they are referring to a battery. When a biology person says cell, they are referring to the biological cell. When maybe policemen say cell, it is prison. When we common people say cell, maybe you are referring to cell phones. So there is lot of meanings, even at the meaning change, or like there are multiple meanings for many words in English or any language. In a language, lexical ambiguity or is the basic or the most first level of ambiguity. Then we have syntactic ambiguity. Syntactic ambiguity means individually the words may not be ambiguous. Ambiguous means unclear. Okay, ambiguous means unclear. I don't have to say it, I'm sure all of you know. But anyway, okay. Syntactic ambiguity means when words combine, there can be multiple meanings. Okay, I'll show you an example and this will be clear from this example. Okay, generally, we call this PP attachment problem. Okay. So here, the first sentence, I saw a girl with a telescope. So this is the phrase that is being attached with a telescope, and it can have two meanings. One is the girl is holding a telescope and I saw that girl. The girl is holding a telescope and I saw that girl. Or it could be I'm looking through a telescope and I saw a girl through it. Okay. Here, if the phrase with the telescope is attached to girl, then it is intended, this is the intended meaning. If the phrase with the telescope is connected to girl, this is the meaning. And but if the phrase with the telescope is attached to saw, then this is the meaning, the first one. So this sentence can have two interpretations. Okay. To understand which is the correct interpretation, we first have to do parsing. So since we have learned parsers in compiler, maybe we all have learned parsers in your compiler classes. We know we can have grammar, and using grammar, I can draw a tree. I can draw a parse tree. I can draw a parse tree from this sentence, and then I can find out which word this phrase is attached to, and from that I can understand this meaning. But again, sometimes the grammar is also very ambiguous. For a single sentence, we can generate multiple trees. This is what we called as syntactic ambiguity. Right? Then there is semantic ambiguity. Okay, semantic ambiguity again is a more higher level of ambiguity. That is, words when they combine, they may not have different trees. It may be a single tree. Okay, the tree may be the same, but still it may have multiple interpretations. So, for example, let us look at this. I saw bats. It's a very, very simple tree. It's a very, very simple sentence with a very simple tree. So it is just a saw and I and bats. The tree is very simple. This is a binary tree you will generate from this if you do a dependency parsing. But since these individual words, there is a lexical ambiguity also here. And when they combine also, there are multiple meanings. Then there is pragmatic. There is ambiguity at pragmatic level, just in the context. Suppose I'm in my classroom and I see a boy who has kept his leg extended, and I tell him, hello dear, can you please hello dear, can you move your leg? If I ask him, can you move your leg? What the actual intended meaning there is, I'm giving him a command to move his leg. Okay. So he is on my way, so I want to tell him, just move aside, I want to go. Can you move your leg? But if a doctor is asking the same question to a patient, then the meaning is different. Okay, in that context, actually the doctor is asking whether that patient is physically able to move his leg. Whether the patient is physically able to move his leg. Understood? Same sentence, but in different contexts, it is meaning different. So these are different levels of ambiguity that can happen in language processing. Now, how do you come up with rules? How do we come up with grammar rules or semantic rules, or how do we come up with algorithms that can actually solve these kind of issues? This makes a very interesting question and has been a favorite topic of researchers for many years. Then there is languages have irregularities. You know, we have sarcasm. Sometimes we say, what a idea. Maybe actually we wanted to say that it is a very bad idea, but we literally, like, we say the opposite. So there are sarcasms, there are idioms, there are metaphors, lot of irregularities. So I'll just show you some examples. Some of the examples like heart of gold, kill two birds, piece of cake, raining cats and dogs, walking encyclopedia, all these. Okay, this is an example of sarcasm, a great movie for a Sunday nap. Okay, what is the sentiment of this? Is this a good comment or a bad comment? A great movie for a Sunday nap. Is it a positive comment if it is a review for a movie? If you see this comment, will you go to watch the movie or not? Are you thinking? Okay, how many of you says good? It's a good review. Let me see. I cannot see when I'm on full screen. Okay. Okay. Yeah. Okay, glad. There are responses. So definitely people are listening. Okay, it is a very, very negative review because we know that movies are not supposed to be, it's not supposed to make us sleep. Movies are not supposed to make us sleep. So it is a bad comment. But now, so a simple task like identifying sentiment of a text becomes challenging when people are using such kinds of words, right? Literally meaning the opposite of what they have written. Then the third thing is language. Language keeps evolving. Okay, language keeps evolving. Meaning of words changes. That is one kind of evolution. Another is new and new words get added to the vocabulary. For example, like even the word Google, okay, it was not there previously. So search was something else. So googling, the word Google, or maybe the word googling, um, tweeting, tweeting. There are a lot of new words that is getting. I'm sure in since we have audience all over India, I'm sure you all will be now able to relate like how the language has evolved. Like from in your childhood, there was many of the words which you use today had either had a different meaning or they didn't exist. Okay. So over the years, language keep evolved. So you need a system which can actually adapt to this. Okay. You cannot have a fixed rigid system and expect it to work fine. Then there are linguistic communication or communication using languages is very compressed. For example, so this is called as missing text phenomenon. That means we all know what we all know, but machines don't. So when there is a speaker and a listener, there is a common knowledge. Okay, there's a common knowledge space that is being shared by both of them, and that is the reason we can communicate with very limited words. So when a person say plastic cup, okay, the listener understands it is a cup made of plastic. And when someone says plastic factory, it is a factory that produces plastic. So even though this made of or produces to hold, to make, all these are not explicitly being, even though these are not explicitly being mentioned in the text, still people are able to understand the meaning. Okay. Coffee cup is not made of coffee. It is it is to hold coffee. But when I say plastic cup, it doesn't mean that it has to the cup is going to hold plastic. Okay. Understood the difference? So this was called missing phenomenon. So when you develop a system, all these missing pieces the machine has to automatically identify. It is not there in that. This is another problem, and I'm sure there are a lot and lot of other challenges. I just have put some of the um, interesting ones here. Maybe there are more boring ones. I'm not going into that. Since we have audience other than from Kerala, maybe I would be interested in knowing what do you think is a very important challenge in your language. Okay, maybe you can think of it, and at the end of the session, we will discuss. During our discussion time, you can share with me what do you think is the maybe not greatest, but at least most interesting challenge in your native language. Maybe we haven't explored something, which maybe it's not a challenge in English, but in your native language, it is a challenge. Or if you want, you can put it in the chat box now itself. We will discuss it during the discussion hour. So now coming to the evolution of NLP. This is just a very quick overview, so we know how we reached here. Okay, so earlier, as I said, it is NLP is a very, very, very early problem. Okay, since 1950s, people have been working on it, and during that time, NLP was mainly rule based. Okay, it was mostly about like if you are doing natural language understanding, you are using grammar rules. Okay, even in India, there were Panini grammar, Panini's. Like there are a lot of other works, like, even especially in Sanskrit and all, there are very powerful grammars out there. So basically, NLP was centered around rules. Okay. The problem was these rules, these were not very scalable. Okay. It was very difficult to come up with rules that was going to work for everything. Maybe you can do it for a very small domain. Maybe I'm developing something for a medical domain. I can come up with rules for medical domain, or maybe legal domain, or maybe on a very small small subset of a problem. Coming up rules was okay, but you cannot have rules that is going to adapt to everything, or maybe generic. That's a problem. And then rules, to write rules, you need domain expertise. Right? Just like if you are developing a chat therapist, definitely you need a psychologist or a psychiatrist who can tell you what are the features that you have to look in the chat. Okay, what are the like giveaways? What are like how do you identify if the person has any psychological problem or something like that, or how it has they have to be handled? Writing our rules require domain expertise. Okay. So after 1990s, we came with statistical NLP. Okay, so this was like a very beautiful era, or very. This is when there was lot of development in NLP, because here the rules were not explicitly defined by a expert. Instead, we were relying on data. We were relying on data. So it was mostly data oriented. Okay. The statistical NLP was mostly data oriented. We had a lot of training data, and we tried to come up, or maybe it was more like a pattern identification. Okay, just like you are identifying patterns in other data, maybe images or tabular data, you are trying to identify patterns from this large amount of data and using statistical rules. Okay, simple rules like naive Bayes to solve this. Here also, the problem was, one is we needed data. From this data, we were learning the rules automatically using programs, definitely using programs. When I say automatically, it's always through programming. We were but still we were relying on handcrafted features. Okay? Rules may not be or need not be defined, but still features had to be defined. Right? That was it. And here also, to define the features, we need domain expertise. Then from 2010 onwards, we started using neural networks. We started using neural networks for processing language, and this is generally known as neural NLP. Okay. So whatever we see around here, though, all those fuss about chat GPTs, Llama 2, and whatever Bing, what else? Okay, whatever natural language processing things that you see now is based on artificial neural network. Okay, so idea is you extract features from the raw data without actually explicitly handcrafting them. Okay. So here both rules as well as features are being automatically identified by the artificial neurons. Just like human brain is identifying what are the important things, the neural networks is automatically. Complex networks like CNN and RNN is using this data to identify the features. Okay. So here no, we don't, or we are not much dependent on the domain expertise. So maybe a quick example, rule-based. So if you are developing a spam filter, okay, this is the most simplest example you can think of. Okay, given an email, the problem is identify it as spam or not spam. Okay? Given an email, you want to identify whether it is a spam or sim. So in olden times, if you are living in if you are a teacher or a researcher at 1950, you'll be writing rules like this. Okay, how many company names are misspelled, whether there are this words like dangerous words like lottery, dollars, Nigerian prince, or something like that. Then you'll be coming up, you'll be noticing whether there is some urgency like hurry up, important, such urgent words are there, whether they are using any inappropriate languages. So you can come up with different rules, whether maybe you want to look at the from email IDs, kind of email ID that they are using. All this from these other, so based on this you can write rules. Right? But if you are in the statistical NLP era, you may be looking at the yeah, this is another example. They'll give a simple example. So in spam filters, you will be looking like, for example, you have some word W1, W2, W3, W3, like for some words. So you'll be counting how many times each of this word occurred in spam. So let us say the word business, the word business occurred in spam email, it occurred 50 times. In non-spam email, it occurred 100 times, right? So like that you can count. You can count how many each of the words and identify what are, like maybe you will just leave out all such is, was, the, which is not important. You may identify relevant words, and then you can get a count. So you can actually count it and find out what is the probability that business, the word business occurs in spam. Right? You can easily do this. You can just find how many total number of words are there and how many times the word business occurred, and then you can find the probability of each of this, and you can use some statistical formulas to calculate what is the probability that email. Okay, do I have that slide? Okay, fine. Okay. You can easily identify, just by counting, you can easily identify whether a mail is spam. So this is another example. This is an example where you're doing auto completion using statistical NLP. Okay, so there is I love chocolate, and you want to find out what will be the word that comes here after chocolate. What is the most probable word to come? Okay, again, if you have a very large corpus, you will be counting, like you will be counting how many times chocolate. Okay. Sorry for the bad handwriting. I'll write neatly here. Okay. So you'll be counting how many times chocolate cake occurred and how many times chocolate occurred. So this is the probability that cake will happen or cake will occur after the word chocolate. So out of 100 times the word chocolate occurred, maybe 25 times cake came after it. Okay, so the probability is 0.25. So similarly, for each word in your vocabulary, you can find out its probability, and just by doing a simple comparison, you can make this. Okay. So before coming of all this complicated BERT, LLM and all, till 2018, Google was using such simple tricks. Okay. Google's NLP was based on statistics. Now, coming to neural NLP, I think I'll have to go faster. Okay. So neural NLP, it is basically based on neurons. So I'm not going into this figure. I'm sure by now you know what is neurons. 2 days you have been learning about neurons and all. You know what is a neural network. So basically the idea is how can you use this neural network to do language processing. So how do we get started? I have been talking about theory and all. So let us now get some real work done. How do we get started? First step is given a text. So this is a text. Given a text, you have to tokenize it. Tokenizing means split it into different tokens. See, I'm not saying split into words because tokens can be anything. It can be characters, it can be word, it can be a subword, that's part of a word. So the key idea is you have to split it. Okay. So if you do character level splitting, these are the tokens you get. If you do a word level tokenization, you get 4 tokens. 1, 2, 3, 4. Okay, you get 4 tokens. If you do subword tokenization, you get 1, 2, 3, 4, 5. 5 tokens. In modern NLP, we mostly use this subword tokenization. We are more interested in subwords rather than word level tokens. There are multiple reasons for that. If like, what do you think is better, or what do you think out of maybe character level? I'm not even asking. It's just a bit complicated. But what about word and subword? Which one do you think is better? So I want to process my text. My first step is I have to split it into tokens. Which one do you think is better? Should I split it as word level, or will it be better if I look at the subwords instead of words? I can hear something. Word level, subword level. Okay. I'll just join through my phone also so that I don't have to stop in between to read the comments. Let me try. Okay. Do you have any justification for that? If I say both of you are right? Why do you think subword is better, man? Anissa, man? What what makes you feel that? Okay,
Uh,
maybe you are right. So you can you can say, tell me,
Maybe
why do you think?
if I want to use some other words after this token, so we can, if so we are using subword recognition, it is better, I think.
Yeah. Yeah, what you meant is, suppose instead of tokenizer, I have another word like tokenization, right?
Yes, ma'am. Tokenization or token generator, something like that. If it is subword, we can add more other predictions for that.
Okay, okay, very good. So if you are using subwords, actually, wait, I have to mute this so that it's not disturbing me. Turn off sound. Yeah, it's good. Okay. So if one thing is, see, in your training data, there may be the word tokenization. There may be another word tokenizer. There may be another word tokenize. Okay. If you are doing tokenization, you are doing it on a word level. All this will be considered as different tokens. Okay. Then in the next step, you may have to do something else to combine this. And if a entirely new variation of that word comes in your inference or testing time, the model may identify it as unknown word. Okay, this unknown word is a big problem both in rule-based and statistical models. Because if you're using statistics, you're using probability. You have the word tokenizer, tokenizing 100 times in your data set, training data. Okay, but in your testing data, the word is token. Instead of tokenizing, it is tokenizer. But this is a new word which you have not seen in your training set. Okay, this will be considered as different. So this is a problem. One problems of unknown words, and but if you are, as ma'am said, if you are splitting it at this level, eh, this since tokenizing is already there in the data, it will identify this as a known token, and it has information about that. And it's I said ing might have come with some other word, for example, synthesizing. Okay. And this ing also, it would identify, assign and the meaning to it, and you can combine these two and get the meaning of tokenizer. So word level is that. Now, see, character level tokenization also happens, especially in like baby name generator. Such projects I have seen. So if you're trying to generate a baby name, maybe you want to do it, or maybe I have thought about this problem. See, I don't know Sanskrit, but like, it's a very interesting language. If you look at it at a NLP perspective, natural language perspective, because like as I said, I don't know the language, but people have told me even words have specific, no, even characters have some meaning. Okay? Even character level, each character has some meaning, and when the characters combine, the word can get a meaning. So if there is someone who's an expert in languages, you can tell me whether it's true or false. This is something which I have heard. Okay. So maybe some yeah, like va has some meaning, ra has some meaning, and then va and ra combined will the word may have may will word the word will get a meaning from its constituent characters. So when you're processing such a language, maybe you should think of doing character level. And I'm sure many other Indian languages will have this phenomenon, which I'm not aware of, which you may know better. So, but in English, this P and H doesn't have any meaning, so I don't see much use in doing character level tokenization. Now, so after tokenization, the next step is converting these tokens into vectors. Okay, so I got the word. Now I want to represent the word as vectors. Okay, maybe the easiest or the most naive, straightforward thing is uh, to assign numbers. Okay, the cute brown fox jumped over the brown dog. So the is number 1, cute is 4, brown is 13. Like that, you assign numbers to each of this, and then you can convert it into binary digits and then feed it into their neural network or do something like that. Okay. This is called as index-based encoding, and I am telling you this is wrong because words have relations also. Words have relations, and these numbers cannot hold that relation. For example, when I say amma, or when I say mother, or when I say mummy, all these are having the same meaning. But if you're using an index-based encoding, amma may have number 1, mummy will have number 57, and mother will have 57, and mummy may have 72, and there is no relation between 157 and 42. So these numbers cannot hold any relation. Or maybe the word little has number 3, word cat has number 5, and you know little cat is kitten, okay, or little dog is puppy. But you cannot find a relation between 5 and 3 and 25. Okay, you cannot come up with ideas like 3 plus 5 is 25, which is not. So this type of representation is not not possible. And you might be wondering why I am discussing it here, but we'll see shortly. We will be using index-based encoding as another occasion. So next is one-hot embedding. Again, it is the same. If you have 1000 words, you will have a vector which is of length 1000, and corresponding to each word, you will put a 1. So 1000 is sorry. So I think it is vertical. Okay. So cat is all zeros, the is 1, all zeros, quick is 0, 1, all zeros, like that. It's called one item. Again, all the same problems is there in this also. Next, so ideally what we want is, we want a notation where somehow if mother is 25, we want mummy also to be 25. Okay. If mother is 25, we want mummy also to be 25, or maybe 25.23 or something like that. Very close, or maybe 26. Okay. We don't want mummy to be 29. And if puppy, is 19 and little is 2, I want dog to be 21. Sorry. Yeah. 21. Or maybe 17. Yeah. I want the dog to be 17 so that I can identify that little dog as puppy. Okay. I want a representation which can capture both of this. Okay. This is where the idea of word embedding comes. This is actually based on, I have that? Yeah. This is based on a concept called distributional semantics. Okay. So in distributional semantics, we represent words as vectors, and we try to represent words in terms of its neighboring words. Okay. So the idea is, you shall know a word by the company it keeps. Okay. It was told in 1957. So idea is, just like we say that about people also, right? When we meet a person, we like, even though we don't know that person, but we know all his friends, we will just assume that, okay, yeah, he's something like that. Okay, if all the friends, all his company or colleagues are very good, we will assume that he's also good. If they are very like, maybe not to our expectation, we may have a bad impression about that person also. So just like that, again, it is a very judgmental thing to do. I'm not in any way encouraging that, but the idea is same. Okay. See, I'll give you another better example. When you are listening to a phone conversation, you might, like when you are talking over the phone, you might not have grasped some of the words. Okay, but still you are able to correctly guess which word you missed, right? Even though you are not, you might not, due to poor connection or something, you have not properly heard one or two words, you will not say repeat. You are able to identify what the word it is because you see the neighboring words, right? Or you are reading something, one of the word is missing, it is not clear, you will be very, very, very easily able to find. Or maybe entirely differently, you see a new word which you don't know the meaning. Okay, that's the example shown on the screen. You see a new word, esguno. I hope that is how it is pronounced. So you see a new word, even though you have not seen that word before. Did you guess what is the meaning of that word? What is the meaning of that word? Have you guessed? Anyone? A drink? Okay. Okay, very good, Adira Vijay. Adira has correctly guessed it. It is a kind of something related to wine. Okay, it's kind of alcoholic drink. So you are able to correctly guess the meaning because you have seen its friends or the neighbors, okay, occurring with the word wine. Okay. You have seen sentences like a bottle of wine is on the table, or you have seen wine makes you drunk, or you have seen we make wine out of corn. Something like such sentences you have seen before. And from that, you are able to guess the correct meaning of this word. Okay. So you are guessing it from its company or the neighbors. Or in our language, in NLP people's language, we call this as context. CONTEXT, context. So you are guessing the meaning from the context in which the word appears. So instead of just assigning some random numbers, you try to represent word in terms of its context. Okay, that's the whole idea behind distributional word representation. So what you see here on the screen is a representation for each of this word. The first word. So what does this mean? See, each of this column refers to the sentence. One is the first sentence, two is second sentence, third sentence, fourth sentence, like that. Okay. So Teskino can occur in sentence one. Loud motor oil tortillas cannot. Motor oil can occur in sentence one. A bottle of motor oil is on the table. Bottle of wine is on the table. Perfect. So like that, each of the dimension is a context. So you are representing the word as a vector, and in this vector, each dimension refers to a context. And now if you closely look at this vectors, you will see that the word Teskino is very similar to the word wine. Okay, so it is matching in first dimension, second dimension, and third dimension. Only in the fourth dimension there is a mismatch. So the most closest vector to Teskino is a wine. So if you are plotting something like this in a Cartesian coordinate system, you will see that Teskino is somewhere here and wine will be definitely somewhere closer to it. Okay, so if you want to find out how similar these words are, you can simply use vector distances like cosine similarity or Euclidean distance. On any vector measurements you can do and find out which word has the closest meaning. This is the idea behind distributional semantics. So yeah, this is one way of representing text. Then when we came to neural NLP, we went one step further and we came up with the idea of neural word embedding. Okay, so neural word embedding is again based on distributional semantics. You are going to represent words in terms of its neighbors, but using a neural network. Okay, I hope the idea is clear. You are going to define the meaning of each word using its context, using its friends. Okay, using in which sentence it occurs, or which documents it occur, or with which words it occur. But instead of counting, okay, here it is count. But instead of actually counting how many times it occurs, you are going to use a neural network to predict. Okay. So the idea is you take a word, you put it into a neural network, and you get a vector out of that neural network. So you might have already learned in your neural network class. So how do you represent a neural network? Something like this. Your output y is w into the input vector x plus b. Right? If you're looking at a single layer neural network, something like this. So if x is some representation of word, you need to have y, which will be neural embedding, which will be satisfying all these properties. So we'll just quickly, okay, it is 7:22. Maybe I'll just quickly say what is neural word embedding, and then we can go for a break, and then we will come back and to learn more about word. So after word representation, we'll stop and then we'll come back and talk about sentence representation. Okay. So neural word embedding, the idea is you have a word, you first convert it into one hot encoding. Okay. So suppose the word is, what's the word? Word is business. Okay. So this is its one code encoding, one hot encoding. It's all zeros and there is a one here and then there is all zeros. You convert it into a one hot vector. So first you do an index encoding. So in the dictionary, the index is 168. And then you create a vector from this. So at 168 position, you will have a 1. And then you will give this as an input to a neural network. And neural network will give you an output, which will be always in a lower dimension. This neural network will give you an output. And this output is the representation for your word business. So if you are wondering how you are going to train this neural network, the idea is something like this. Let us take maybe what you can do is tell me a word which has the same meaning as business, or maybe I'll just go with dog and puppy. It's very easy, right? Dog and puppy. Okay. So if I put dog into this neural network, I should get a number. If I put puppy into this neural network, I should get another number. And this should be similar. That is what I said, right? These two numbers should be very close because dog and puppy are really having the same meaning. So idea is you find out pair of words which is co-occurring with dog. For example, dog, eat, right? Dog, sleep. Dog, bites. Okay. This is, you will generate this from your training data. You don't even need label data. You can take any text, Wikipedia or textbook, or you can take any document and then find enough number of words which is co-occurring with dog. Okay. Similarly, you can find enough words that is co-occurring with puppy also. So puppy eats, puppy sleeps, puppy bites. Okay. I'm sure all the words that is occurring with dog will occur with puppy also. Okay. Words like shutdown or charging or meow or something like that. What else? Yeah. There are, will not happen, right? Battery low. Such words will not happen with dog or puppy. So whatever words is occurring with dog will be occurring with puppy also. So idea is you give each of this as input to the neural network. Okay. So in your neural network, you will first input dog. You will get a vector. Then you will you have two neural network. One is for encoding dog. Another is for encoding context. Okay. Yeah. Okay. So you will have one neural network which is going to learn encoding for the word dog, and you will have another neural network which is going to learn an encoding for its context like eat, sleep, bite, etc. So what you do is you will try to minimize the distance between these two vectors. So here I am showing in blue color. In blue color there is dog, okay, and in red color there is eat, okay. So initially, when you know, right, neural network, initially it's all random values. You don't have any specific value, and then you start training it. Only then the weights get adjusted. So initially the dog and eat is very far, but you start updating the weight of neural network and try to make this vector closer. So once you start training, what happens? The word dog will start moving closer to eat. Okay, but similarly you have another vector, something puppy somewhere lying somewhere here. Okay, again very far. Okay, but you are training with all this data. So what's happening, this vector is also getting updated and this vector is also moving closer to it. The values is constantly being changed each time you are updating the neural network. When I say updating, what I mean is training. When you are training the neural network, this vector, values of this vector keep on changing, and then this dog starts moving closer to it, puppy also starts moving closer to it. Okay, so after sufficient training you will find that both puppy and dog will, both puppy, dog, cat, all this will come closer to the word eat. Okay, but this is not about eat also, you are doing it for every other words, right? Maybe there is another context word. Again, context word I am representing in red. So that's another context word called charging. Charging. Okay, so can you tell me two other words which is going to move towards the word charging? Maybe laptop, cell phone, maybe your EV car. So all this will be coming closer to this vector. So by using a neural network, you are initially using random vectors to represent words, and then you are adjusting the vectors so that it will become closer to it, to come closer to its context. So finally you will find that similar words will have similar vector representation. So see, actually this is a bit more complicated thing. I have tried to make it very, very simple because this is your first experience in NLP. I don't want to scare you. Okay? But once you get the idea, it's actually very simple. What you're trying to do is you're just trying to maximize the dot product. Okay, it is just vector dot product. If you are a mathematician, you can think of it as V dog is a vector and C eat is a vector. What you're trying to do is you're taking the dot product of these two vectors and you're trying to minimize this value. Sorry, not minimize, maximize. Okay, and I say minimize because I'm always thinking of the loss function in network. Okay, so vectors will have maximum dot product when they are closer. Okay. So that's about word vectors. So what next is, now you know how to represent words. So now you know both mother and mummy and amma will have closer vectors, right? And the very interesting property is, if you take the vector for little and you subtract it from the word dog, so you will get something like this: V dog minus V, or maybe plus V little, is equal to V puppy. Okay, so this is a very interesting property. And another most promising thing about word vectors is you don't have to do anything. All these are readily available as pre-trained vectors, pre-trained models. Okay, the most popular one is word2vec. It is from Google. You have GLOW, which is from Stanford. GLOW stands for Global Vectors. You have fast text, which is from Meta AI, Facebook, initially Facebook, now Meta AI. So all this, they have already trained all this and they have posted it for us to work on. So there is two options. Either you download the model and then use your own data set and you train it and get your own vectors. A more easy and better option is you directly download all the vectors and directly use it in your project. You don't have to know anything. Okay. I'll show you an example here. See, this is from GLOW. GLOW. This is the vector for king. Okay. The very high dimensional data. This is how the word king is represented. Okay. So that's all about word representations. Let's go for a break, and when we come back, we will see how we can go one step further and try to come up with vectors for sentences, because as I said, language is ambiguous. Even though sentence words have individually meaning, when they combine, they will have a different meaning. Right? There can be ambiguity. So how can we go one step further and combine these vectors to capture the meaning of larger text like sentences? That is where the RNN and all such CNN and all such things come from. Even transformers, I'm not going, it's not my duty to teach transformers. So I think it will be having it in tomorrow. Transformers also does the same. It is for learning sentence representations. So thank you, audience, for the interactions. Thanks for answering all my queries. It makes me happy. So let's go for a break. When can we join? Maybe 45? 10 minutes break will be enough, right?
Yes, ma'am.
Yeah,
You
we
can
can
join
come back
at 7:45. Okay, ma'am.
7:45.
Okay.
Okay,
Okay,
thank
ma'am.
you.
Thank you.